Hello, my name is Barry Ezel. I'm a Senior Principal Analyst at Innovative Decisions, and I'm here today to present to you an example of a multiple objective decision model. But it's not your typical multiple objective decision model. It is a quantitative value model that has incorporated uncertainty um, in two ways. One, uncertainty through the weights, and that seems reasonable since if you're building a joint model, you probably wouldn't get perfect agreement upon what the weights and preferences are in a quantitative value model among services. And the second thing is that we've shown how uncertainty can be modeled with scoring, um, and how that scoring can be aggregated through simulation. And so this quantitative value model isn't the typical type that many have seen in the past. It's actually a quantitative value model that's coupled with a simulation. And so as we talk through it, the one thing that we consider an innovation with this particular model is the fact that to deal with, I guess, disagreement among potential different stakeholders with what the weights of the model will be, we've implemented a Dirichlet distribution in the weights and a technique for sampling from that distribution so that the properties of a quantitative value model will work appropriately. And so just to orientate you to the model, this is the quantitative value model here. We're calling this pilot model a force structure value model because it's calculating value. And this is an additive preference model, meaning that the weight of a particular measure is multiplied times the value returned for a particular score of a system, and then added up across all measures. And when you do that, you end up with overall value for a particular system. So for example, I'll just highlight a cell here. This is 65 is a raw score for air-to-air. Just so happens that 65, that's an actual measure, which is the number of aircraft destroyed air-to-air. But down here, it's been transformed into value. And to look at the calculation more closely, you see here that the raw score of 65 is calculated in this particular algorithm here. And so we have the weight of the particular measure multiplied by the interpolated value of the x-score into the v of x score using this particular algorithm here. It's actually a piece of Visual Basic code that's built into the Excel spreadsheet. And when you add these up, you end up with overall value. And when you add up all the systems in your portfolio, you end up with an overall value score here. So down here, I've just done some accounting. I've sort of racked and stacked and categorized things. Overall, we're finding here, you see I'm just adding up the measures here, added the measures there. There's another example here for these calculations. And so it's a very simple model, and the purpose here isn't to bedazzle anyone with a very complex quantitative value model, but rather to show a couple of techniques that we've determined through elicitation of stakeholders and through interviews with you and others that any future model that's a defeat needs to be able to deal with uncertainties. So we wanted to demonstrate some of those techniques here. Now, the first thing I want to do is I want to talk about the Dirichlet distribution. If you look up here, as you know, weights have to sum to 1, but immediately you notice, uh-oh, they don't sum to 1. That's because here we have a distribution on this, and we've modeled, I guess, a range of values for multiple stakeholders using a triangle distribution. And the same here and the same here. And so what we do is, as the simulation runs, we draw values from each one of these distributions. Output is down here. You can see the calculation here. We simply take the value that's drawn from the simulation and we renormalize it so that the proportionality of it always sums to 1. And the same thing down here for the measures as well. Now, that's how we deal with uncertainty in value preferences and weights in a model. Let me tell you how we deal with differences in scoring. This is a pretty interesting technique here that we've developed. We're using, this is an example of the weighted linear opinion pool, and we can combine scores in data by simulation using the linear opinion pool. In this particular example here, I want to call out a few things. First, in this particular example, we have input from an expert, we have input from campaign model XYZ and campaign model ABC. And in this notional example, we've assigned a weight to the expert of 0.2, 0.3 for this particular model, and 0.5. And that sort of represents our belief in the overall merits between these three things here. So essentially here we go in and for expert, for system 1, you see for air to air, he's able to provide a minimum, maximum, and most likely value. And in fact, he's done this for all three systems across all measures, which is very nice. Looks like this particular study here, the output of this model ABC, I was able to do the similar thing, I was able to determine min, max, and most likely. But interesting thing here is that for model XYZ, we only have a min and a max as an output for systems 1, 2, and 3. And so in the example here, here's how the algorithm works. So here we have this particular assumption modeled here for system 1. Expert, the measure is air to air. It's a triangle distribution. And you can see we're pulling those values down from here. But look here, we have this situation here where we don't have a triangle distribution. This is more appropriately modeled as a uniform distribution. And down here we have 3 values, and that's more appropriately modeled as a triangle distribution. And so here is the forecast or the output. Once I do the weighted linear pool algorithm through simulation, I end up with system 1's blue-red exchange ratio, which is the number of red aircraft that are lost. And so I'm essentially convolving these 3 distributions, and I'm combining them with respect to these weights over here and their draws from their distribution. And the output then is a new distribution, which then becomes an input into my value model. Okay, so I'm going to go ahead and run the simulation. Let's see what we have here. One of the first things we notice, this is total value for the force structure here. It's the sum of all 3 systems in the entire portfolio and their overall value. Down here we have how system 1 is performing, system 2, and system 3. In this graph here, it's interesting to see how in the simulation how things move around, and sometimes system 1 outperforms systems 2, and sometimes system 2 outperforms systems 3, but almost in every case it seems like system 3 is outperforming 1 and 2. And then down here, here's another view, typical bar graph that you see in Excel. And the idea here is that it's not just a simple discrete calculation of value. All right, it's a simulation that's dealing with uncertainty in a couple of dimensions. And so whereas the weighted linear opinion pool algorithm for aggregating distributions has been around for a long time, combining it here in this type of assessment, as well as what we think is innovation in using a Dirichlet to sample 3, or actually n number of distributions depending upon the number of measures, allows us to deal with uncertainty in a very novel way that, at least from the literature, we haven't seen before. So with that, I'll stop here. This simulation, let's see, it's about ran its course, and when it does, you'll have these final values here. And if you're familiar with crystal ball or at risk, you know that there are a million things you can do with it. The data, export data, look at all sorts of different scenarios for every distribution, for every output. So It's a typical package. There's nothing special about it other than it was convenient for us to be able to demonstrate some of the concepts that have emerged from the interviews. That defeat's got to be able to deal with uncertainty. In this type of simulation environment, we can certainly do that. So at this point, I will turn it back over to Russ. Thank you very much.